Citation of Professor Sneashish Chakraverty. Professor Chakraverty is a distinguished mathematician, academic leader, and internationally recognized researcher in the areas of applied mathematics, machine learning, structural dynamics, and computational modeling. He currently serves as professor in the Department of Mathematics at the National Institute of Technology, Rourkela, India, where he has played a pivotal role in advancing academic excellence, research output, and institutional governance. Professor Chakraverty received his Bachelor's of Science honor in Mathematics from St. Columba's College, Ranchi University, followed by an MSc in Applied Mathematics from the Rourkela University, where he secured first rank and a university gold medal. He further earned an MPhil in computer applications, again standing first in the university, and completed his PhD in applied mathematics in 1992 with a thesis on vibration and computational methods, which was adjured meritoriously. His early academic brilliance laid the foundation for a career that seamlessly integrates mathematical theory with real-world engineering application. He pursued postdoctoral research at two premier international institutions, the Institute of Sound and Vibration Research, University of Southampton, UK, and Concordia University, Canada, with his additional academic engagements at McGill University. These experiences significantly shaped his research in computational mechanisms, vibration analysis, and numerical methods. He later served as visiting professor at several leading universities worldwide, including Johannesburg University, South Africa, and universities across Europe, North America, Africa, and Asia. With over 35 years of combined teaching, research, and administrative experience, Professor Chakraverty has made seminal contributions to applied mathematics, artificial intelligence, soft computing, and dynamical systems. He has authored an exceptional body of scholarly work comprising over 350 journal publications, over 160 conference papers, 39 books, and 70 plus book chapters, and hold patents in applied computational technologies. His research has been widely cited, placing him among the top 2% of scientists worldwide in artificial intelligence and image processing for multiple consecutive years. Professor Chakraverty has successfully supervised 30 PhD scholars, guided numerous postgraduate projects, and hosted international visiting researchers. He has led 22 sponsored research projects as principal or co-principal investigator and continues to mentor young researchers across disciplines. His work bridges rigorous mathematical foundations with emerging paradigms in machine learning, uncertainty modeling, and fuzzy dynamical systems. An accomplished academic administrator, Professor Chakraverty has held several key leadership positions at the NIT Rourkela, including the Dean Academic Affairs, Dean Student Welfare, Professor advising the Director on Finance, Head of the Department of Mathematics, Head of the Central Library, and Chairman of multiple statutory and academic committees. He has also contributed nationally as an external state member of the NIT Padrish and the NIT Agatha. His role in shaping institutional policy includes chairing the formulation of NIT Rourkela's anti-plagiarism policy and the implementation of the National Education Policy NEBP 2020 framework. Professor Chakraverty's professional recognition are extensive and prestigious. He is a senior member of the IEEE, president from 2015 to 2016 of the Mathematical Science section of the Indian Science Congress Association, and the recipient of numerous national and international awards, including the CSIR Young Scientist Award, the Careers 360 Faculty Research Award, and multiple IOP Publishing Top Cited Paper Awards. His scholarly impact has also been acknowledged by Scholar GPS, ranking him in the top 0.0% of scholars globally in vibration and physical sciences. Widely sought after as a keynote speaker and invited lecturer, Professor Chakraverty has delivered lectures at more than 50 international and national universities and conferences. His current research interest focuses on mathematics of machine learning. Thank you. You're welcome, sir.
Yeah, thank you. Thank you for introducing. So thank you for giving me the, I think I'm audible. Yeah. Am I audible?
Yes.
Yeah, yeah. So let me share my screen. Okay. Is it visible? Is it visible?
It's coming up.
Yes.
It's coming up.
Yeah, good, good.
Yes, full screen. Yeah.
Yeah, it's fine.
It's coming up.
This is fine.
Yes, it's fine. You can go ahead, sir.
Okay.
Yes,
Okay. So first of all, thank you very much for giving me opportunity to present my this research topic. So and thank you for so elaborately mentioning about my credentials and citations, etc. Thank you again, and very good morning to all of you as per your place, and very good afternoon in India. So anyways, so I will just light upon as the title is shown here, that is machine learning in dynamical systems, a mathematical journey from exact to fuzziness. So here actually I will try to ignite your minds in different directions of your mathematical modeling, namely in machine learning that may be applied to different dynamical systems, and also I will light upon the fuzziness of those systems, means uncertainty of those systems. Okay. So first of all, if you see about the nowadays artificial intelligence, everybody knows more or less. So this is actually the bigger set. So in that we have machine learning. So we have different types of machine learning. Okay. So those are, suppose, artificial neural network. Then you have SVM, support vector machines. Then if you go to optimization techniques, then we have genetic algorithms, then swarm intelligence. So there are many. So it is a combination of all these learning methods. Even statistical learning, those are there in machine learning. So in machine learning again comes one, that is one method that is called artificial neural network. And in artificial neural network we have a special type of learning, that is deep learning. Okay. So mainly I will be focusing on artificial neural network models that will be were used to solve different types of dynamical problems. And those dynamical problems are actually coming from, means the governing equations. Equations are the differential equations, and sometimes those differential equations can be converted to eigenvalue problems in general. Okay. So, and moreover, you'll see that some uncertainty also I will take in those parameters, and then how to handle using the machine learning, namely uncertain, means artificial neural network, how it handles the uncertainty in the problems, that also I will show you. Okay. So with this, the main means topics will be these ANN, and you know that ANN actually, that is artificial neural network, is actually the machine learning. Means we have the natural neural network in our human body, and that actually is being mimicked in computer. Means scientists trying to mimic those neural networks in computer, and then it is called artificial neural network. So there are actually various applications of this artificial neural network, namely in variety of problems. Nowadays, each and every many areas actually these machine intelligence or neural networks are being used, such as in physics, chemical, medicines, finance, and there are many. Some of them I have written here. And few recent applications include also astrophysics models, buckling analysis that is related to civil and mechanical engineering, then inverse kinematics problems, etc., etc. Okay. So ANN is actually key component sometimes for dynamical solvers that I will show you after a few minutes. So this is the actually figure of a basic model of ANN. So if you see, so here actually what happens, these x1 to xn are the parameter of the problem. Okay, so if I have n parameters, input parameters, and final output parameters is z. So if I have data, suppose n input data and 1 output data, then the artificial neural these nodes I can generate like this: y is equal to b is bias, and bias plus the summation of this xi with some weights for these connections. Suppose from x to this bias term, so it will be b plus summation xi wi, that is your y. So it is a simple means ANN model. Okay, that's a simple model. So error will be this half into summation target output, means I have the final output exact data and final output from this model data. So this I subtract and square and sum for all those data. Okay, so this is the error. If this error is not satisfied, then again I will go here in this means this weights will I will change. Okay, suppose W1 plus delta W1, or there are actually procedures to change this. And again, I will find this Y for this model and go on this finding these errors, and will stop when this error is minimized as per your means desire. Okay, as per the means requirement of the problem. So this is the just simple model. So actually we have, there are many things. Actually in this short time I cannot mention all those things. So this is only one actually, there is no hidden nodes or hidden layer. Okay, so you see now in an architecture are different types, maybe feed forward or feedback. So the left hand side figure 1a, the feed forward neural network, and right side figure is feedback neural network. See here, this signal flows from these nodes to the last nodes. Here you see the signal flows last nodes, again it also gives in the previous node. So that's what is feedback neural network. And we use here activation function. So activation functions are also various types, that is identity function, Gaussian function, sigmoidal function, tangent hyperbolic function, rectilinear, linear unit. There are many. Okay, so actually in my work I have used these two: unipolar sigmoid function, this is the figure, and this is tangent hyperbolic function. These two types of activation functions we have used in our work. So learning rules, as I told, there are learning rules. So we have supervised and unsupervised. Supervised means when I have output data, I have a teacher, so I know the output, but I have to fit those data. That is called supervised. I can fit by regression also, if those people who knows about the regression. So actually this is similar type of regression, but not exactly that regression. Okay, so as we have in regression method, we have input and output data. Here also supervised, we need the input and output data. And then the unsupervised, that means learning without a teacher, means I don't have any output data. Suppose I want to solve a differential equation. So I don't know the actually the solution of that differential equation, but I know the initial or boundary condition. So using those conditions, we can solve that using artificial neural network or machine learning using unsupervised learning. Okay, so this is the difference between supervised and unsupervised. Now there are various types of learning rules you can get in many of these books. All these I am not going to these details. So maybe Hebbian learning rule, perceptron learning rule, delta learning rule, then other two. There are many others also. But in our work, we have used delta learning rule or back propagation rule. So now I will show you a simple problem of solving transcendental equation. Okay. So I hope you know what is transcendental equation. So I have a single equation, a1 phi 1 plus a2 phi 2 plus up to n pi n is equal to c. Simple one variable single one-sided transcendental equation. So I will make this means architecture of this ANN like this.
It's your sensor. Hello, Prof. Your mic is muted. Can you kindly unmute yourself, sir? Hello, sir. Your mic is muted, sir. Kindly unmute your mic. Yeah, yes, sir. Carry on. Your mic, sir, is muted. Kindly unmute.
Yeah, this is okay, fine.
Yes. Okay. Okay. Yeah. Go ahead, sir.
Yeah. Okay. Just a minute. Yeah. So it's okay now. You can hear. Yeah. Am I audible?
Yes, sir.
Yes, sir. Go ahead,
Yeah.
sir.
Yeah. So this is the model for the single transcendental equation. So I will now show by an example about this latter. So before that, if you have system of transcendental equation, means I have a n number of equations. You can see I have a11, phi1, a12, phi2 up to a1 and phi n with all additions is equal to c1. Next equation is a21, phi1, then a22, phi2 like that. Means phi2 means phi x2. Phi 3 means phi of x3 like that. So is equal to C2, and last equation is an1 phi 1, that is an1 phi x1, then an2 phi 2, then up to an and phi n is equal to Cn. So this is system of transcendental equation. N equations and n unknowns. Then I will make this architecture like this. So you are seeing here this layer having n variable x1, x2 up to xn, and these phi i's I have like this phi 1 to phi n. Okay, so then I have, depending upon what are the coefficients here, a11, a12, so we'll put these as the weights a11, a12, etc. Okay, then we train this using delta learning rule, and I can solve this transcendental equation. So this is through machine learning. Okay, so this I can show you now by one example, simple example. So if we consider this transcendentally one equation, single equation, cos square x minus x is equal to 0. So I can put this in an architecture like this cos square x here, this x here, and the coefficients are 1 and minus 1, 1 and minus 1. And this first is, this is the x to this cos square is x as weight 1, and x to x this is 1. So like that I can train and I can solve. And in this figure 6 in the below right hand side, you can see the convergency plot of the root of the transcendental equation. Okay, so this is actually, if you see in the next slide, sorry, so this is actually the root is, if you can see which has a root of this equation, exactly we can find by other method, Newton-Raphson or other method. So 0.6417. So if you can see here, this root is 0.6417. You can see the figure. It is exactly, it is actually matching that, and convergency comes after 200 epochs. Okay, so in this way, simple non-linear, this transcendental equation I can solve using neural network. Okay, this is just a simple example, means using ANN or machine learning. So if I now have means this I can also solve in like that. I solve you the theory system of equations also. So I am not showing that due to the because we have already solved these things, and the papers are available corresponding to this. So I am not showing you all those examples. Okay. So now coming to eigenvalue problem. Suppose I want to solve eigenvalue problem like this, which is actually dynamical system, this mx double dot plus cx dot plus kx is equal to 0. So dynamical systems, we got this type of differential equation. This is a coupled second order ordinary differential equation. This M is a matrix actually, and this C is also a matrix and K is also a matrix. This M, as per the structural problem, this is called mass matrix. This C is called damping matrix, and K is called stiffness matrix. And there is a pattern of this matrix depending upon the problem. By the way, this for this structure problem, this is just a diagonal matrix having the elements M1, M2, means the mass of that problem means that n degrees of freedom. So these are the masses placed. Okay. Similarly, this damping matrix is tridiagonal matrix, and stiffness matrix is also tridiagonal matrix. Okay, so this is the problem that I want to solve using neural network. So if I don't have this damping, so this equation 5.1 can be converted to 5.2. That is only mx double dot plus kx is equal to 0. So this I can convert into eigenvalue problem, putting x is equal to phi to the power I omega t, considering that this follows simple harmonic motion. And so it leads to a linear eigenvalue problem given by equation 5.3. Ax is equal to lambda x. Now I want to find this lambda. That means I want to solve this eigenvalue problem where lambda is eigenvalue and x are the eigenvector. So both eigenvalue and eigenvector I can find using this machine intelligence technique. So if I expand this after putting the A elements, so what I will get that everybody knows means this will get a characteristic equation of nth degree depending upon the order of the matrix. Okay, so this way I will get this as the characteristics equation. So this is again actually equation depending upon your a1, a2, a3, an these coefficients. Okay, nth degree equation. So this I can solve like that. I have already shown like this, putting this lambda, lambda square, lambda cube, etc. in this layer 3, and this I was earlier putting x here in place of x, it is lambda. So I can have put here lambda, and like that a1, a2, a3, this coefficients I put, these are the weights, and from this input layer to the middle layer I'm putting all these at 1. And again, if I can solve, if I solve this neural network, so I will get I will get the solution. Okay, so now coming to an example, so suppose I have this 3 degrees of freedom system. So this, these are the masses of 1 kg, 2 kg, and 3 kg. I have different spring coefficients. So this, if we do the physics of all these, so I will get A, that is M inverse K, because I have already found, I've shown here, see, here it is M inverse K. This is I have put as A, okay? So M is mass, K is stiffness. So M inverse K. So this I can have for this example like this, is M inverse K. So this matrix comes out to be this. So this is a third order matrix. So I will get the characteristic polynomial as 3 lambda cube minus 11 lambda square plus 10 lambda is equal to 2. So it is third degree equation. So now I can put this in the ANN architecture like this, because I have lambda, lambda square, and lambda cube. So I have lambda, lambda square, and lambda cube in the third layer, and these are connected to the output node as the coefficients of these. Okay, so these are lambda coefficient is 10, so here 10, lambda square coefficient is minus 11, so it is minus 11, and lambda cube coefficient is 3, and the input layer to middle layer or hidden layer, the weights we will put arbitrarily as 1. So if I train this, so I can get the solution. So if you can see this table, so these are the actually the solution. Okay, if you see the last column, so these are the eigenvalues. Okay, because we need in ANN different parameters, so learning parameters, stopping criteria means I already told about the error up to which we should run the program. Okay, and initial weights also we have to give. So these are the initial weights. So lambda 1, lambda 2, lambda 3. Finally, I got 2.3874, 1.0, 0.2792. And these are the epochs where these eigenvalues, when it starts converging. So in this way, I can find just an example, I can solve the dynamical problem with respect to the structural problem that I have shown you. Okay. And correspondingly, eigenvector also we have found for lambda 1. This is the first eigenvalue. Lambda 2, this is the second. And this is the third. For the third eigenvalue, this is the eigenvector using the same procedure of NN. Okay. Now coming to actually an application problem. Suppose I have a 5-story building, okay, Shear building. Okay, we assume that these are the assumptions, just that story masses are M1, say first story, second story, third story, up to 5th story. So these are the masses, suppose given as M1 as 30 kg, M2 as 27 kg, like that. And these walls I will consider as springs, and those spring constants are k1, k2, k3 up to k5. So this is I will get then the matrix as fifth order, and if I have the characteristic polynomial which is fifth degree, now this again I can put in, as I already told, this I can put in an architecture and I can solve. And the solution for these eigenvalues are like this. In this table 3, the last column gives you 5 eigenvalues, and the figures, these are actually with respect to the convergency of these eigenvalues. Fine. So these are eigenvectors for the 5 eigenvalues that also we have computed through ANN technique. Okay. So now see these, what we have done till now, we have just got the eigenvalues, that means frequency of the system. Now I will show you a practical, practical problem with respect to civil engineering, that is response prediction of multi-story buildings subject to earthquake motions using artificial neural network. So what happens, you see, when somewhere earthquake triggers, so what happens when earthquake triggers, here different types of waves travels through the soils. Okay, soils means in soils we have different types of means rocks, sands and metals, or maybe coals or ores or whatever is there in the soils. So these waves travel through these soils, okay, through the ground and comes near to the building. Suppose there is some structure, so whatever waves it will travel, so it will now change when it will come to the structure. Okay, so now these waves, there will be a soil and structure interaction. So as per American Society of Civil Engineering, till now there is no mathematical model which can actually handle or which can predict that what this means. This, suppose what will be this soil and structure interaction means, what type of wave or what will be the acceleration of these waves in the building or the structure. So that is very difficult to obtain. Till now it is not there, that model exactly. Okay, so here we can use this artificial intelligence or neural network in the machine learning. If I have here the sensors or some equipment, I can measure the waves here, and I have the equipment here with sensors in the building, and what are the displacements here. Now these are the, suppose, input, and output is the building sensors. So I can play with those, and then for different earthquakes, future earthquake, I can predict by what this displacement will be by what amount, so that I can develop an earthquake warning system. Okay, so that thing actually we have actually did little bit of work on that direction. So we have taken exactly the actual earthquake data. So in India there were several earthquakes. Okay, so these types of earthquake data we have taken. So see, this is the multi-story structure, tall building, and this is a Chamoli earthquake, Barkot in Himalayan region, it is there. Okay, so this peak acceleration is 19.588 centimeter per second square. So this type of earthquake, it triggers on the ground. So when it travels to the structure, this is changed actually. So suppose here the some equipment is there which can capture the displacement of these flows. Okay, so if I have those displacement and this displacement or acceleration, whatever, so if I play with that, then I can fit that, then you can predict for different earthquake, other earthquake or some other magnitude earthquake, what will be the displacement or acceleration of this structure or building for this case. So for this some mathematical modeling, here it is the equation 1. If you see, earlier we have seen mx double dot plus kx is equal to 0. Right hand side was 0 because there was no force. So now it is minus ma double dot. A double dot designate the acceleration for the that earthquake. Okay, so if I model this, I will get this equation 2, and this I can solve using this Duhamel integral, we call it. So this I can solve and find the displacement. So actually, see, for we had the measurement, or we had the data for the earthquake, but not the data for the buildings. Okay, so this building displacement we have found using this model. Using here, you see inside that I have the earthquake acceleration, and this is sine omega t minus tau. Omega is the acceleration, natural frequency. Okay, natural frequency of the structure. So I can find this integration, and then I can play with this input and output data. So this earthquake we have taken as the input, and different types of earthquake also we have taken, Uttarkasi earthquake, Chamoli, Bhuj, etc. So then we are actually, I am not going to show you all those work, just some representative problems or figures I will show you. So this is the multi-story shear building, suppose, and these are the parameters. Parameters means mass matrix and stiffness matrix. I have already defined. So these are the mass matrix where this 6,000, I have taken all the masses of the stories as same, and this is the stiffness, okay, Newton per meter. And using that model now, if I have input output as the acceleration of the earthquake input and output at the acceleration of the building for different story. Now, if you can see the top figure, that is 8th floor. So I can find the actually exact acceleration also we have found using some numerical technique, that finding this integration. Okay, and then using that we have found the ANN acceleration, and then we have plotted both, but you see the beautiful matching. Okay, although we could not go actually in some of the peaks, but at least the trend it is gaining, okay, using ANN. And this figure is for 8th floor. Okay, similarly, if the lower one, bottom figure, it is for 6th floor. Similarly, we have actually simulated many problems, maybe other stories also. Okay, so this is another for 80% of the earthquake. Here it is 120%, means different means magnitude, means whatever. Suppose I have 6.0 magnitude, then from that we have computed 80% of that, and then we trained, and here it is 120% of that. Then how it behaves, or how it actually gives the trend for that acceleration, that also we have predicted, okay, using that. So these are not that whatever I am presenting, it is not that fully whatever models and step by step I am not showing, because it will take much time. I just want to try, I want to trigger your mind that this machine intelligence can be used in these directions, in all the dynamical problems, whatever. If you have the data or you don't have the data also. Without data also, we have solved directly the differential equations, but I think that I am not showing in this lecture. But those things also we have done. Okay, so this is for some other earthquake. Okay, in another direction, any direction like that, and using different actually errors also we have plotted, errors and without damping. So those things also we have done. So till now, whatever we have seen, that was without any uncertainty. As you know that in our day-to-day problem or other problems, we have uncertainty in all of the problems. Whatever problem you take, there will be uncertainty. So uncertainty can be handled by many ways. So one way is this interval and fuzzy, and another is that probabilistic or stochastic. Okay. So we have not used probabilistic or stochastic. We have used here interval and fuzzy, and that too interval and fuzzy in the neural network. That is why we are calling this as interval and fuzzy neural networks. And again, we will case study with some dynamical problems with respect to structural dynamics. Okay. So and moreover, why we have used this interval and fuzzy, when actually you have less number of data, then we should use the interval and fuzzy. If you have large number of data, then you can use the probabilistic or stochastic analysis. Okay. So I'm not going into these details, just few things. Interval, actually all the data, suppose in interval form, if you see the data, suppose x is your some variable, so I can have x lower and x upper, where x lower less than equal to x less than equal to x upper. So this x will be in between lower and upper value. So remember, this left side is lower value and right side is upper value. So now we have specified addition, subtraction, multiplication, and division, means formulae or definitions. So if I want to have two addition of two intervals, so this is simply lower and upper. But if you subtract, then it will be a little bit different, lower minus upper and upper minus lower. That is why if I subtract x minus x, means suppose two intervals, same intervals, we subtract, then we will not get 0, 0. Okay, and that is the problem with this interval computing. Okay, although this is very challenging, with respect to your practical problems to handle uncertainty. But this x minus y and this x by y, means x divided by y, is also a problem, because if you see this x divided by y, we do this, but where we assume that this y tilde should not belong to 0, means 0 should not belong to this y tilde. Okay, so these we have to take care before applying this interval computing, and that too in NN, so it will be a little bit more difficult. Okay, so then comes to fuzzy set. Fuzzy set also a type of uncertainty. So this is an ordered pair where we have element and its membership function. Okay, and an interval actually is a subset of fuzzy set. And we then comes to fuzzy number. Actually, fuzzy number is coming from fuzzy set, a special type of fuzzy set where the membership degree is convex, normalized, okay, and piecewise continuous. So we have different types of fuzzy set, okay, fuzzy number. So we have used some particular type, okay. So like triangular fuzzy number. So the shape is of triangle, if you see, and we write it as ABC. And that ABC can be written in terms of interval. That is why I have first shown you the interval definitions. So this fuzzy number I can write in terms of interval. So then that means we need to have the interval computing. Now this is another type of fuzzy number that is called trapezoidal fuzzy number. The shape is of trapezoidal and we designate by ABCD. You see here ABCD. Again, this fuzzy number also can be written in terms of interval, and then we can handle with interval computing. Okay. Now coming to the same type of problem, that is multi-story structure. So you see here earlier the masses, if you see earlier it was in this mass matrix as M1, M2, Mn. Now you can see here I have in interval form M1 lower, M1 upper, M2 lower, M2 upper, up to Mn lower, Mn upper. This means these are uncertain form, having lower and upper values. Similarly, I have K matrix also, stiffness matrix, that is also in terms of uncertainty. Okay, so interval form. So after substituting, supposing that simple harmonic motion, etc., will turn into again to an eigenvalue problem. Like this: k minus m omega square phi is equal to 0, and see every all these matrix and whatever parameters I am using, all are with tilde. That means all are in interval form. Then your that's ANN model. That is, now it will be interval neural network model. So here, if you see the left hand side, these are the inputs. Again, these are all uncertain form. That is lambda 1 tilde, lambda 2 tilde, lambda I tilde. Here it is k1 tilde, k2 tilde, kk tilde. Here the problem is knowing this frequency or the eigenvalue, what is the stiffness if I want to find. So in this way, I can have the neural network architecture, and using those data, I can find what is the stiffness. Okay. So similarly, for fuzzy case, we will have actually in terms of this interval, means converted interval from the fuzzy, and I can handle this uncertain case. Okay. If you see again here in the figure, you see here mass is here not only M1 lower and M1 upper, but I have another element here, that is M1C center. Okay, because I have taken triangular fuzzy number. So all these masses and stiffnesses, I have three components. Although those we have converted to interval form. That is why in the mass matrix I have interval form of these elements. Okay, M1 lower H, M1 upper H, like that. Similarly, K matrix also I can write in terms of interval. Okay, like this. K, this is the K matrix. So if I again do the all calculations, etc., I will come into this equation 3.4. That is again an eigenvalue problem, but having this interval form. Okay. So this is the fuzzy neural network. I have now in terms of H actually designate that conversion from fuzzy to interval. Okay. So lambda 1 H2, lambda I H, depending what is your I. Okay. And these are the hidden nodes. Hidden layer. In the hidden layer, I have these are the nodes, and this is output layer. Okay, so if I train that, then again I can find for different unknown frequency what is the stiffness. Fine. So now I suppose I take some example. So if I take, suppose it is a 5-story with uncertainty, interval uncertainty, so K1, K2, K3, etc., K4, K5. Suppose we take like these elements, lower and upper, okay? And then if I train, etc., so these are the trains for different data numbers. So these are the K1, K2 we have means computed, okay? K1 to K5. Right. So you see here the solution is K1 n and K1 desired, K2 n and K2 desired, etc. We have found. So this is the result. So now coming for, oh sorry, this was actually in crisp case. When we did the crisp, so we took the center value. Okay. Now next figure shows the interval one. So this is the interval case. So this is, see, left side figure with lower values, and right side figure, left side figure is lower and upper for K1, and right side figure is K2, means second stiffness for lower and upper. Okay, and the comparison between desired and neural network, and see the trained and the data means data matching are good with respect to your NN and desired. Okay, and this is again for K3, K4, and K5 because it was 5-story building. So we had 5 stiffnesses. Okay. So this is for testing. After training, suppose I take some new value of these interval stiffness are taken. So these are the comparison. Okay. So this is fuzzy case. Fuzzy case again, I will take as this same data. Okay. So these are the fuzzy case comparison for K1, K2. So here you see K1 lower, K1 lower desired, K1 lower fuzzy neural networks result, and K1C, that means center value, okay, for desired. K1C for fuzzy neural network, like that. The three are there, lower, upper, and center values. Okay. So now testing for fuzzy case. These tables are for testing for this fuzzy case. So we have tested for those data which are not used in the training. Okay. So what actually till now what we have done, actually these just representative results we have shown here. We have simulated for various cases, various actually practical whatever means problems also we have done. Okay, so using different earthquake data also we have done. So in the conclusion, so you have seen that ANN models are means actually dynamical solver. As a dynamical solver we can use. We have used means we have compared the traditional neural method, numerical method, and ANNs, and you can see that ANN is computationally efficient. Okay, and the model is messless, because if I solve by different problems using some other method, suppose finite difference or finite element method, those are we have to use meshes and all. Here we don't need mesh. Okay, so it is like a black box. If I train the neural network model, and then if I give the input data and new input data, then it can predict approximately what will be the output. So that is the actually benefit of this machine learning. So okay, so due to the nature of the neural network, the CPU time for finding the solution of the given equation does not increase exponentially with increase in dimension. There are many things. I am not posing those things anyway. So these are the some references, okay, that we have followed. Okay. These are the actually some books that we have with my students actually we have written. That is, first one is Artificial Neural Network for Engineers and Scientists. So in that book you will get all solving ordinary differential equations, how to solve using neural network and all. And the second one, Applied Artificial Neural Network Method for Engineers and Scientists, solving algebraic equations. In this book you will get different types of transcendental equation, eigenvalue problem, even nonlinear eigenvalue problem also we have solved in this book. Okay. So these are the two books, one from Taylor and Francis, CRC Press, other one is World Scientific. And then we have, this is actually concepts of soft computing. Here we have included some programming also related to fuzzy and ANN. Okay, there we have used the uncertainty, etc. And this is the soft computing in interdisciplinary sciences. This is edited book. This is not, those 3 years are authored book. And this is one journal that is we are actually I am the chief editor of this, Fuzzy Computation and Modeling International Journal. published by Science. Okay, and thank you for your attention. Just I have gone through the models actually regarding all machine learning techniques with respect to artificial neural network. I tried to ignite your mind at least that this can be used in any other problems also where you have the differential equation or you have the data. You can use very well, but again it depends upon how you take the what optimization techniques you are using, how many nodes you are taking, how many inputs you have, how many output you have. There are many things to play in that with that actually in the simulation it requires. Then about main thing is the weights, how you are generating and what type of learning algorithm you are using. So there are many challenges now. Actually, now we are working in physics informed machine learning also. Okay, where we have used with data the physics of the system. Okay, that I have not actually presented here. So if I get chance in future, I can again detail about that. Okay, thank you very much.